Hello everyone. In this lecture we are gonna study engine measurement and performance. We have bore and stroke. The bore of a cylinder is simply its diameter measured in inches or millimeters, and the stroke is the length of the piston travel between the TDC or top dead center and BDC bottom dead center between them. And bore and stroke determine the displacement of the cylinders. When the bore and stroke are of equal size, the engine is called a square engine. Engines that have a larger bore than a stroke are called over square, and engines with a larger stroke than bore are referred to as being under square. Over square engines offer the opportunity to fit a larger valves in the combustion chamber and use longer connecting rods, which means over square engines are capable of running at higher engine speeds, but because of the size of the bore, the engines tend to be physically larger than the under square engines. Under square engines have short connecting rods that aid in the production of more power at lower engine speeds. A square engine is a compromise between the two designs, and the crank throw is the distance from the crankshaft's main bearing center line to the connecting rod journal center line. So the stroke of any engine is twice the crank throw. We have the displacement. A cylinder displacement is the volume of the cylinder when the piston is at BDC, and engine displacement is the sum of the displacements of each of the engine cylinders. So typically, an engine with a larger displacement produces more torque than a smaller displacement engine. However, many other factors influence an engine's power output, and engine displacement can be changed by changing the size of the bore and or stroke of an engine. We have as well the compression ratio. An engine stated compression ratio is a compression of a cylinder's volume when the piston is at BDC to the cylinder's volume when the piston is at TDC. The compression ratio is a statement of how the air-fuel mixture is compressed during the compression stroke. So it's important to keep in mind that this ratio can change through wear and carbon and dirt buildup in the cylinders. Also, the higher the compression ratio, the more power an engine theoretically can produce. Also, as the compression ratio increases, the heat produced by the compression stroke also increases. So gasoline with a low octane rating burns fast and may explode rather than burn when introduced to a high compression ratio, which can cause pre-ignition. The higher gasoline octane rating, the less likely it's to explode. As the compression ratio increases, the octane rating of the gasoline should also be increased to prevent abnormal combustion. Also, we'll discuss right now the engine efficiency. So we have a different factor to measure the engine efficiency. Let's start with the volumetric efficiency. Volumetric efficiency describes the engine's ability to have its cylinders filled with air-fuel mixture, and if the engine cylinders are able to be filled with air-fuel mixture during its intake stroke, the engine has a volumetric efficiency of 100%. Typically, engines have a volumetric efficiency of 80 to 100 if they are not equipped with a turbo or supercharger. Basically, an engine becomes more efficient as its volumetric efficiency is increased. Also, we have the mechanical efficiency. Mechanical efficiency is a measure of how much power is available once it leaves the engine compared to the amount of power that was exerted on the pistons during the power stroke. Power losses occur because of the friction generated by the moving parts. Minimizing friction increases mechanical efficiency. And we have the thermal efficiency. Thermal efficiency is a measure of how much of the heat formed during the combustion process is available as power from the engine. And we'll discuss right now what's the difference between torque and horsepower. Torque is a twisting or turning force. Horsepower is the rate at which torque is produced. An engine produces different amount of torque based on the rotational speed of the crankshaft and other factors. And also we have the mathematical representation in this graph shown here. This graph shows that torque begins to decrease when the engine's speed reaches about 1,700 rounds per minute. Brake horsepower increases steadily until about 3,500 rounds per minute. Then it drops. The third line of the graph indicates the horsepower needed to overcome the friction or resistance created by the internal parts of the engine rubbing against each other. Brake horsepower is a term used to express the amount of horsepower measured on a dynamometer, and this measurement represents the amount of horsepower an engine provides when it's held at a specific speed at full throttle. So horsepower is also expressed as SEE, gross horsepower, which is the maximum amount of power an engine produces at a specified speed with some of its accessories disconnected or removed. So SAE, net horsepower, represents the power produced by an engine at a specified speed when all of its accessories are operating.